Hello? Hello everyone! Today we will continue to look at the content of HCI-Storage. Today, our main focus is on a very important concept in the field of storage, which is address mapping management. This concept is actually very important in both traditional mechanical hard drives and solid-state drives. First of all, we need to clarify two concepts. The first is our LBA, which stands for logical block addressing. To give an analogy, you can imagine a storage device as a library, and the logical block address is like the shelf number in the library, or an index number for the books. It can point to the address of a specific data or data block. Or it points to the data block corresponding to a certain address. This is our logical block address. Now the second one. The physical block address. As for the physical block address, this address is equivalent to what? It's equivalent to the exact placement of each book. Is on the actual shelf in a library, for example. Like, we describe an exact location, like Tokyo at a certain longitude and latitude. It actually represents the actual physical location of the data on the storage medium. These are our two different types of locations. One is the logical block address, and the other is the physical block address. How do these two addresses manifest in our different storage devices? First, let's talk about traditional mechanical hard drives. In mechanical hard drives, our logical block address and physical block address correspond one-to-one. And this relationship does not change at all. Why? Because our physical device is essentially composed of several platters, right? This is like a library with a fixed layout. The number of each book and its position on the shelf are permanently bound. This is how our mechanical hard drive works. Moreover, it has a characteristic of using an overwrite method. So if we need to write new data, the new data will directly overwrite the existing data, essentially replacing the original data. The physical block and logical address. In fact, both the physical and logical aspects are the same, so either term can be used. It's like when we modify a document on a mechanical drive, the new document content will directly replace the old document content. This is a basic characteristic of the disk, right? Everyone has probably heard about this, right? There are some issues with repairing data on mechanical drives, but this repair is not always 100% effective. What are the requirements for this? Essentially, if you want to modify or repair data on a mechanical drive. First of all, you must avoid the issue we mentioned earlier, which is overwriting. Because with mechanical drives, it's about overwriting, gesehen. If the physical block address of the data you want to repair is overwritten by other data, then it's basically impossible to repair it. If there is no overwriting, actually, you can still repair some data by following the traces on the mechanical hard drive. This is a basic characteristic of our mechanical hard drives. They use overwriting. However, solid-state drives are quite different. In solid-state drives, our physical addresses and logical addresses are different and not fixed. This is because our solid-state drives have a unique storage characteristic. They do not support overwriting. If you want to write new data to a solid-state drive, you must first erase the old data before writing the new data. What is this method called? We generally refer to it as garbage collection, similar to replacing a book in a special library. You can't just place a new book in the spot of the old one. Instead, you need to clean the spot thoroughly, and then find another suitable place to put the new book. In this way, it's actually no longer a normal library. So this is how it is. Now in solid-state drives, how do we deal with physical addresses, right? And logical addresses, how exactly do we distinguish them, or who is responsible for it? Handling this complex conversion task, this is where we use our FTL, which stands for Flash Translation Layer. The FTL is like an intelligent librarian. It knows the data of each book, its index number, and its actual placement, and it can assist when a user wants to access this data. To quickly locate the position of the data, specifically, it means our users access the solid-state drive through what? Through our logical address. what does each logical address represent? It represents 1. Generally, the size of a sector is 512B, and our operating system usually accesses the solid-state drive using 4K as the unit. Here, we refer to the basic unit of user access to the solid-state drive as a user page. Inside our solid-state drive, between the main controller of our solid-state drive and the flash memory chip, it is based on our flash configuration as the basic unit for access. We generally also call this flash page as the physical. When each user writes data, the main controller of our solid-state drive will find a suitable physical page. Then it writes our data into it. At the same time, inside our solid-state drive, a mapping is recorded, a mapping relationship, which is like, hey, when a librarian places a book in a new shelf location, they will. Our record will note it down. It could be recorded anywhere, right? Recorded on the computer, recorded in the ledger, for example, noting down the book's number and which position on the shelf it was placed. That's the idea. And it's the same with our data. It's equivalent to asking what the index number of this data is. And which position on the disk we placed it. That's the idea. With this mapping relationship, the next time a user comes to read this data, the solid-state drive can accurately know based on this recorded information. From our which position on the disk to retrieve the data from. For example, when you open a file stored on a solid-state drive on your computer, the operating system uses what? It uses our logical address too. Send a request to the solid-state drive, and then the solid-state drive looks for the mapping relationship. After finding the physical address, right? Then we read the data and provide it to the user. This is basically our process. Address mapping management actually has some impact on the performance and lifespan of our solid-state drives. Due to the update mechanism of the solid-state drive and the existence of the FTL, the storage location of our data on the solid-state drive keeps changing. To ensure that our solid-state drive can work efficiently and stably, some optimization strategies are needed, such as wear leveling strategies, which essentially allow our solid-state drive to. The various storage units, that is the erasure and writing of flash memory cells, should be as uniform as possible. We briefly mentioned this earlier, right? This is to avoid certain storage units from wearing out prematurely due to excessive use. This way, it prevents you from continuously using one block. If you wear out one block, it becomes completely unusable. So here, it's like we are ensuring that all the blocks in our entire disk are used evenly. For example, today I use you, tomorrow I'll use it, and the day after tomorrow I'll switch to another one. By switching and erasing like this, our overall lifespan will be extended. The overall lifespan will be extended. This is equivalent to, for example, needing to use all the bookshelves in a library evenly, right? If we only use one bookshelf, it might lead to that bookshelf, right? Because of the frequent taking out and putting back of books, it could cause damage to the books. Or the bookshelf, wear and tear on the bookshelf, and other such issues. Including our FTL, which can also perform garbage collection operations. As data is continuously written and deleted, solid-state drives will generate some invalid physical pages. These invalid pages are like the space occupied by old books, cleared out by library management. The garbage collection operation is essentially about migrating the valid data from these invalid pages to new physical pages, and then erasing these invalid pages to free up space for new data to be written. This is our address mapping management. This technology is essentially a crucial link connecting logical addresses and physical addresses. It has different forms and working mechanisms in our solid-state drives and mechanical drives. Both are very important, but they are not the same, so everyone should distinguish between them. FTL, as a core component of our address mapping management, ensures efficient access to the solid-state drive and accurate read and write operations by recording and maintaining the hardware relationship between logical and physical addresses. This is our address mapping management. It plays a significant role for both types of hard drives, so everyone should be familiar with it. Alright, if anyone needs to learn Washington technology or wants to obtain the Washington question bank, please send a private message. I can also leave more comments below the video for technical exchanges. Well, that's it for today.